I agree with you, but what do you mean? Just so I can help everyone understand. Okay, so you're going to take like the x and y coordinate here, and you're going to subtract the x and y coordinates from here. And that answer will be a vector. Okay, good. So u will be, it will have an x and a y component. The x component is the difference between, let's see, this is A, this is B, and this is C, right? So since we're going from B to C, we are going to take the C numbers, the x and y coordinates, and we will subtract the x and y coordinates here. So this computation is going to be 5 minus 1, and this computation is going to be 4 minus 4. Understand? And so we get the vector 4, 0. All right, how about the vector v? What's the computation for the vector v? So now we're going from B to A, right? From B to A. So we're going to take the A's and subtract the B's. So it'll be 1 minus 1. And then what's the next component? 1 minus 4. And when we do that, we get 0, negative 3. So we have u and v, don't we? And now let's go to this formula, and let's try and compute it. We know that theta, which will be the angle between those two, right? Theta, this angle between these two, should be arc cosine of u dot v. So when we dot these two vectors together, what was the formula for it, for dotting them? Multiply x with x, okay, 4 times 0, and then add 0 times negative 3. So we get 4 times 0 plus 0 times negative 3 over, okay, over, that I realize that's going to be 0, okay? But the next part would be the magnitude of u. Do you remember how we get the magnitude of u? Square root of that x component squared plus the y component squared. So this is just 16, and square root of 16 is 4. So you get 4 here, 4 times, and then what's the length of v? 3. And this down here is 12, but that doesn't matter because 0 divided by 12 is 0. So theta is arc cosine of 0. And what is the angle? What would the angle be when on the unit circle? Well, we have to look at cosines only. Arc cosine is only defined in the top two, right? So at what angle is your x coordinate 0? Pi over 2. So theta must be pi over 2, which is 90 degrees, isn't it? Therefore, this is a right triangle. Got it? That would have worked. Like we would always get pi over 2, wouldn't we? If this top was 0, wouldn't we? And that top can only be 0 if what? The dot product is 0, right? Well, that's a major theorem that we have in terms of dot product. It says this. It says that, so this is a theorem. It says given two non-zero vectors, u and v. What do I mean by non-zero vectors? Yeah, they have some direction. They've got some magnitude on them. You can't, remember there is a zero vector? So as long as the vectors we're talking about, they're not the zero vectors, then given any two non-zero vectors, u dot v equals 0 implies that u and v are orthogonal. Now, the word orthogonal is the word that we use when we are trying to say that the angle between two things is 90 degrees or 40 or pi over 2. So that really means perpendicular, all right? So if you take two vectors and you take their dot product and you get 0, there's no more work to be done. The angle is 90 degrees, all right? Now, this actually works the other way around too. U and V, if U and V are orthogonal, then U dot V equals 0. And let me change something up here in this one. When I wrote this down, I want to just put in front of here, if this is true, if that's true, I'm going to change implies to then. Okay, so look at these two statements right there. Are they saying the same thing? I guess my question is, did I really have to write both of those? Could I have just written one of those and we would have been okay? Yeah? What I'm going to tap into here is a little bit, any computer science majors? Okay, so this has to do with logic. Think about the logic here. I'm asking you right now whether or not I'm being redundant by saying these two ways, or if it matters. Like if I say this, then I'm asking you, if I say this top one, do I have to say the bottom one? Or if I say the bottom one, do I have to say the top one? That's what I'm asking you. And what I'm telling you is that these are completely different. These have completely different meanings. They're completely different. Now, I'm going to try and illustrate it for you with an example. All right. We may have talked about this. I feel like we have. If you live in the state of Texas, then you actually live in the United States. And let's not talk about citizenship. Let's just say physically, if I'm standing in Texas, right, then I am standing in the United States, at least today, right? Yes? Okay. Does it work the other way around? If I'm a U.S. citizen, then does that mean I'm standing in Texas? It does not, right? These two things do not mean the same thing. So if I were to come up here and just write this first one, that means that if I take two vectors and dot product them, that means they're orthogonal. Guaranteed. What this up here does not say is that if I take two orthogonal vectors, that their dot product has to be 0. Come on, this is logic, so I want you to understand the difference between those statements. If the dot product of two vectors is 0, then they must be orthogonal. But that doesn't mean that just because you're orthogonal, your dot product has to be 0. If you're in my class, then you are in pre-calculus, right? Does that mean that if you're in pre-calculus, you're in my class? No, right? This statement says if the dot product is 0, then you must be orthogonal. But that doesn't mean that if you're orthogonal, the dot product has to be 0. There might be some vectors out there that are orthogonal where their dot product is not 0. But this theorem says that both of these directions are true, which is, I'm saying the opposite now. I'm saying if they're orthogonal, the dot product has to be true. I mean, it has to be 0. Understand? The theorem is giving you both ways. It works both ways. Understand this or not? Okay, so in mathematics, when we have that happen, where it works, if it works in one direction only, like this direction only, then what we write is this. This implies that that's true. Okay? If it works in both directions, then I do that. And that means that if this is true, that has to be true, but you could do it backwards. If this is true, that has to be true. This is called a double implication. Or sometimes you'll see books put if and only if. IFF means if and only if. That means both way implication. It's a very strong condition to have both ways implied. You don't always. All right. Let's, we have from that a very simple way of checking whether or not two vectors are orthogonal, right? All we have to do is see if the dot product is 0. If the dot product is 0, we're done. Another example. Find angles of this triangle. I'm just going to label these points. 1, 1, 5, 6, and 9, 3. Now, I want us to appreciate right now the difficulty of this problem without the concept of vectors. How could you do this using trig and trigonometric functions and things that we've learned already up to this point if you're not allowed to use the dot product at all? You could use maybe like law of cosines or something like that, right? Yes? Because remember, with law of cosines, if you have a triangle and you know this side A, B, and C, right? If you know those, then you can get capital A by using the law of cosines, right? What's the problem, though, with that? I mean, it can be done. You don't know the sides, do you? Now, could you find the distance between these two? You could. You could go and try and find the distance between these 2 points. There is a distance formula for finding the distance between 2 points. It's the square root of the difference of the x-coordinates squared plus the difference of the y-coordinates squared. You could do that. But then you'd have to do that for all these, right? So you're going to be doing a bunch of squaring and square roots and all that stuff, right? The dot product should allow us to get this, though. So what I'm going to do is let's find this angle first. We'll call that angle theta. If I'm going to go after that theta, what am I going to need to do? If I'm allowed to use the dot product, what am I going to need to do first? Create the vectors. And those vectors that you're going to create are going to go from this point to this one and this point to this one. Let's call those u and v. Okay? Now, what is the vector u? 4, 5. Okay. What is the vector v? 8, 2. Good. We're going to need to know their dot product, aren't we? So let's go ahead and get the dot product now. Dot product is, you're going to do the x parts multiplied, so 32 plus the y's multiplied, 10, so 42. That's the dot product, right? What else do I need for this formula? I've erased the formula. Theta was equal to arc cosine of dot product of u and v over magnitude of u, magnitude of v. So I need those magnitudes. Let's go ahead and get them right now. What's the magnitude of u? Well, it's the square root of that squared plus that squared. So 4 squared plus 5 squared, which is square root of 49, 40, 16, and 25, 41. Okay, we need the magnitude of v. Which is square root of, okay, 68. Okay, that's it. Now we just need our calculator, all right? Because we know that theta must be arc cosine of 42, that's u dot v, over root 41 times root 68. So we get our calculators out, and make sure you type that in correctly. And let's go ahead and get the answer in degrees. So make sure you're in degree mode on your calculator, which I am. Arc cosine. Make sure you're using arc cosine, not cosine, right?
Sir,
Yes.
but do we really have to do that? Like the magnitude? Do we know the dot product is 42? So the angles don't do it. Like, you know what I mean? It's supposed to do it.
It's not 0, but all that tells us is that this is not a right triangle. The instructions are to find all the angles of this triangle. So I actually want to recover every single angle in this triangle. We know that this angle is not 90 though, right?
Yeah.
We know it's not 90. So it's not a right triangle yet. It could be that the other two angles, one of them could be 90 still, right? But I didn't design this problem to have any angles that were right. So let me see. I'm getting 37.3 degrees approximately. Okay. All right, so that worked out okay. Let's go after another angle. We only need 2, right? Because once we have 2, the third one's going to come by default. We have these vectors, right? We can't reuse those, though.
I mean, when we take like angle B, or I mean point B, which is 5, 6.
Okay, you want to go after this one? Can I call it beta now instead?
I mean,
Yeah.
we already have to just have the reverse of
I need a different color.
or the
Yeah, so it's the negative of u, yes. Okay, so look, I'm going to go after beta now, all right? For beta, I'm going to create 2 new vectors. They both have to emanate from that point. So one vector here, and then another vector here, like this, right? Let's call this vector right here w. And this one, I could call the green one coming down this way anything I want, but it's the opposite of u, isn't it? Opposite direction. And remember, if you want to change a vector's direction, you multiply it by -1, and it changes the direction. So this green one, I could call it negative u, couldn't I? And then I'm going to go through the same setup. I'm going to figure out what's negative u, what's w, what's the dot product, what's the magnitudes of each one, and then we'll put it all into that formula. We'll get our calculator, and we'll compute it. So what is negative u? It's the opposite of what we had. -4, -5. Okay, good. What is the vector w? 4, -3. Biggest mistake I see on this is that students do these backwards. When you're trying to find this vector w, they go 5 - 9, 6 - 3 instead of the other way around. Okay, let's dot these two together because we're going to need it. What's negative u dotted with w? Getting a -16, right? Plus 15, which is -1. This is the first time we've had a negative dot product. And just so you know, think about it this way. If I have two vectors, what's their dot product if they're orthogonal? 0. If the angle between them is smaller than 90 degrees, the dot product will be positive. If the angle between them is bigger than 90 degrees, the dot product will be negative. So right now, our dot product being negative already is telling us that the angle between these two is bigger than 90 degrees. Now, I don't know what it is, but it's going to be bigger than 90. And you can tell from the picture, it looks like it should be, right? Okay. So, and why would that be? Why would that be? Well, because we're dealing with cosine, right? And the only way for cosine to be negative is if you are in the second quadrant. So it makes sense that we should have that happen. All right, now what about magnitude of negative u? Same one, right? Root 41. And now the magnitude of w, oops, it's not what I meant to write. Magnitude of w, what did you say it was? 5? Oh, nice. Okay, so then we come over here and we say beta is arc cosine of negative 1 over root 41 times 5. And then beta, this was theta, beta is going to be, what do you get? You got some? No? $141. Anyone else 141? No? Okay, I guess I shall type. Okay, 141? All right, 141 degrees and some change maybe, but we'll just go with 141 degrees. Good enough. And then if that is those two angles, right, then we can find our third angle by just doing 180 minus those two. So let's call this one alpha. It's small, right? It's a very small angle. 30. What is it, 1.7? Okay. Well, my drawing is not to scale. Did you get something different? 91? Okay, yeah, I better do this. I'm not trusting that 141 right now. Negative 1 over 5 times the square root of 41. 91.78. 91.8. All right. You're probably not putting your parentheses incorrectly. When you did the negative 1 over, you need all that stuff, 5 times root 41, all in parentheses. Okay, change this. Thank you. What? That was, I'm glad you said something, because my drawing didn't seem like it should be that small for alpha. 91.8. That makes a little more sense. Okay, so add those 91.8 plus 37.3, and then take that away from 180, 50.9. Okay. Questions? You okay with that? Here's what's really, really nice about this, is that in this class, we have been dealing with vectors that are two-dimensional, right? Like I didn't cover three-dimensional vectors in this class. But imagine that you had three-dimensional space, okay? So this is like three-dimensional, like the room, okay? And you have 3 points sitting in space in this room, and you create a triangle. So imagine I pick, let's say, the corner of this chair, right? That's 1 point. Let's say that the projector is another point, and let's say my cup right here is the third point. I can create a triangle between those, can't I? Now, if I asked you to come in and measure the angle, right, between here and there, right, this angle, then it's a triangle, but it's all tilted and stuff, right? So if you try and do this without the idea of a dot product, it's extremely difficult to do. But it's the same procedure. All you do, like let's say that's that little towel. Here's my cup, here's the projector. I just create the vector here, call it U. Create the vector here, call it V. I dot them, I find their magnitude. I take the arc cosine, I'm going to get the angle. And all you need to know are where those points are in space. And the computation is pretty clean. So it's very, very useful for three-dimensional, especially, because you can make a pretty tough problem relatively easy by using the vectors. All right. So what now?
Talk about it.
Yeah, let's call it a day. What are we going to do next week?
Probably review.
We need to talk about the final, right?
Yeah.
We need to actually get ready for this final exam. I do want to talk about maybe one more thing. I think this stuff, you won't be upset to see this on the final. I mean, this is probably stuff you'd prefer to see. So there's another concept that has to do with polar coordinates, where I can just at least introduce you to polar coordinates. And that stuff, I think, again, is stuff you would be happy to see on the final. So maybe we spend about 3/4 of the next class talking about that. And then we try and spend the entire Thursday next time talking about nothing but final. And my goal this weekend is to try and create a review for the finals for my classes, except for Cal 3. Sorry. Well, you're here, so I can't say that. I don't want to say that. I just told them that I'm going to give them a review this weekend. Like, I'm going to make a review for them. But you're in here, I don't want you to think that that applies to your class. Okay, all right, good, all right. Okay. Okay, but I do intend on giving you some sort of guidance on what to focus on, because we've covered a lot of material, so I will give you something to go with. All right. You should see about doing the homework for dot product. See how it goes.
Sir, have you given the third exam back?
The third exam, didn't I last time? I did, right? No? Oh, no, because I thought I forgot it. And then I wound up being in my backpack the whole time. And then I brought them today. So if you want your exam, they're here. Come on up. I'm going to turn the camera off. You texted me, right? No? Who was texting me about their grade?